Hi, my name is Nils Lindstrom, and I'm a kidney biologist at the University of Southern California. There is an urgent unmet need for new therapies addressing the debilitating prognosis faced by all the patients who are diagnosed with end stage kidney disease and currently live with the harsh reality of dialysis and kidney transplants being their only therapeutic alternatives. So, restoring kidney function using stem cell based kidneys would considerably change these patients' lives. What is it that an artificial kidney needs to do? Well, normally kidneys take in blood, and about 1 million nephrons in each kidney filter your blood. Nephrons are these long, thin tubes that at one end connect to the blood and filters it, and the rest of the tube then reabsorbs nutrients and maintains water balance so that at the other end of the tube, it can connect to a drainage system and lead excess water and unwanted metabolites into the bladder as urine. And to build a fully functioning artificial kidney, we need to replicate each of these different functions. But the challenge is that we can't yet build artificial kidneys. And those kidney like structures that we do make, they're tiny in comparison to the fist sized kidneys you have in your bodies. So, how are we going to overcome this challenge of scalability and functionality? Well, as it turns out, in the case in almost all scenarios, nature has provided inspiration for how to solve this challenge for us. And if we turn to some of our very largest mammalian cousins, the whales, as their enormous bodies evolved, they didn't just make bigger and bigger kidneys. Rather, what they developed were hundreds, if not thousands, of smaller individual organs. So if you look at this image here, which is an image of a fin whale kidney, the second largest of all the whales after the blue whale, what it shows is what appears to be almost a bunch of grapes, with each of these grapes being a fully functioning kidney that's on one hand connected to a blood supply and also connected to a common drainage system. So I know you might be asking why this solution could work for us. My lab's expertise is understanding how the kidney develops before birth. And we then apply the insights we gain to generate stem cell derived artificial kidneys. And we have developed a system where artificial nephrons form synchronously throughout thin cellular discs. Each of these miniaturized artificial kidneys is roughly the size of a pea, but it's packed full of 400 to 500 nephrons. So, to provide context to this number, just 1,000 of these artificial kidney discs would contain about 400,000 nephrons. And that number amounts to approximately half the number of nephrons found in each of your kidneys. And critically, this is also close to the number of nephrons needed to keep you off dialysis. So, we can then think about each of our artificial kidney discs as being directly analogous to the grapes in the whale kidney. And therefore, this makes it a problem of scalability. So, our challenge is that we need to make our nephrons more mature and then plumb them in the correct way so that they connect to the blood supply and the drainage system. But realizing that we don't need to solely rely on the normal self organizing principles that give rise to kidneys during development, we started to discuss this project, realizing that we don't need to solely rely on the normal self organizing principles that give rise to kidneys during development. We started to discuss this project with a group of synthetic biologists in Leonardo Marsute's lab. Leonardo Massoud is located at the University of Southern California, where my laboratory is situated. So, synthetic biologists, they think deeply about how we can deconstruct biology and then re-engineer those parts of it that we want to fit our own needs. And together we started to think about this question. How can we drain an artificial kidney and at the same time change how they develop to form functional cell types? The solution that we came up with was that we could engineer synthetic cells and place them together with our artificial kidney discs in a way that they can communicate with each other and then make the hundreds of nephrons in each of those kidney discs reach out and begin to make connections with the synthetic cells. As an example, here is one of our artificial kidneys where we use synthetic cells to instruct the kidney to form connections for drainage. And these nephron tubules, you can see, they begin to respond to a come hither signal and then make these specialized cells that begin to make connections and plumb the nephrons into the drainage system. And as we're making great progress on engineering artificial kidneys that can drain, we're using the same principles of applying synthetic biology solutions to drive cell-to-cell interactions and making sure that our artificial nephrons will also interact with the blood supply. And in the spirit of KidneyX, asking us to think bigger, better, and bolder, we anticipate that this prize will propel our work forward at considerable pace, and we look forward to sharing our progress with you. Thank you for your attention.